All right, so where are we kind of currently at? And I'll kind of come back to this later. We've got that set of kind of sample questions here. So I said I wasn't going to release that quiz until after we talked today, just because there was a couple questions we might not cover. So I put that next problem set up. I wouldn't start it during class, but we've also got that next quiz, which will be up there. You can kind of work on that, both being set to be due at the end of the day, come next Friday. Okay, so those sample questions go along with that quiz. Probably, I think, based off what we did, there should only be like one question that you might not be able to answer until after today's class, but I didn't want to get it out there and someone start it and then not really be sure. So you'll have that problem set. I'm hoping we can do actually a little bit of work on this today. It looks like the files aren't syncing up to my OneDrive. Hopefully it's just taking some time. By the time we get there in class, they'll be sitting there ready for us to go. If not, I'll come up with another way of doing this. I got my laptop, so I can kind of hook it up. But we're not quite there yet because we still have to finish up the slides. So we left off talking about measurement error. Okay. So before we jump into material, so that problem set, the quiz should be kind of the only current thing that's out there. I've sent the grading file to my TA, so hopefully you'll start to see kind of some of those problem set 4s popping up, being graded over basically from now until Tuesday's class. Other than that, any questions for me before we dive into material here today? No? Okay. Okay, so where did we leave off? So we were talking about measurement error, and we said that it really doesn't matter if we have measurement error in our independent right-hand side X variable. What did that do to our coefficient? So if it was just random, it pushed it closer to 0. So if it was negative, it became a smaller negative value. If it was positive, it became smaller. So here with classical measurement error, we said what kind of bias existed? Attenuation bias. It just was a fancy word for it pushes it closer to 0. Okay, so we don't like it, but at least we know we're just understating effects, right? It's always better to kind of understate, right, what's going on, or kind of undersell, over deliver kind of idea. Now, if we have classical measurement error, right, this goes back, I think I gave the example of people self-reporting their intelligence, right? People of lower intelligence levels may give you an inflated or a positive measurement error, while individuals who have higher intelligence tend to give you a negative measurement error. So there, the measurement error is correlated with that X variable. That classical measurement error assumption is violated. So when we were going back, and I said, I'm never going to make you guys do this. Where is it at? Here it was, right? Kind of what that attenuation bias hinged on was that our error, measurement error, was not correlated with those X values. So that was classical measurement error gave us the attenuation. If it is, well, then part of this additional bias isn't going to just go away because that covariance of X with the error term is not 0. Right? So that's going to cause our bias to be really, could be positive, could be negative. You know, could we have a higher, could have a lower estimate? We could see the sign of the estimate flip. We don't know. Right? I mean, technically, I could push you to like actually put a sign to it, but I'm not going to push you guys that far. All I may expect you to know is if you have non-classical measurement error, we don't know what the bias is going to be. Okay. So here I kind of left the slide open thinking about if we have measurement error in that independent variable that's non-classical. Okay. So the file that we were using was this data issues file. I think here, oh, I didn't save it. So we'll go open up that life expectancy data. Kind of come down here. We were looking at classical measurement error last class. So we kind of left off right here, right? Now we're going to look at non-classical measurement error. Okay. So my non-classical measurement error, I'm going to kind of use these hypotheticals. So let's say I'm creating this measurement error, which is, it was reported, so I think we're still looking at GDP and BMI, but somehow BMI, the measurement error that existed, had this added component, so it was completely random. So if we go up here, I'm going to generate, I'm going to copy this down just so we have everything in the same area for today's class. We're going to generate this measurement error, which is just completely random. Okay. Now, if our measurement error in the variable, though, is this completely random component, but a part of our measurement error is not just random, it depends on the value of BMI. So notice here, when BMI is higher, what's going to be true about my measurement error? If I'm adding in 0.1 times BMI, when BMI is higher, my measurement error is going to be higher. So they are correlated. So I can kind of generate this measurement error, right? And so I've got measurement error 2. I could also then create the variable. So this is my measurement error. I'm going to do this hypothetical where I create, let's assume I only have the variable that has measurement error in it. So what I'm going to do is take the original BMI values and put in this new measurement error. So this is kind of a weird scenario where I have the actual data and I'm artificially creating measurement error. In practice, we would only observe the variable with measurement error in it, right? We don't have the luxury of having the actual BMI values. So I've created this new variable. I'm going to run my regression. Now, this is because we're going across 2 classes. I want to have the actual values regression to compare to, right? So if I were to run this regression of GDP or BMI on GDP, I get a coefficient estimate of, it's pretty high, 6.01 times e to the -10. So actually, what did we do last class? I think we used this so that the values just get a little bit easier to work with. So I'm going to come down here, kind of remind us what we were doing. Go back up here. I'm also going to grab this because we used this last class to make sure we're all using the same random numbers, right? So, okay. Oh, did I go down too far? I sure did. Sorry. I'll copy and paste these where I wanted them. Where were we at? We were all the way up here. There we go. So I'm going to set that seed. I'm then also going to copy down. And you could just go back up and run these lines of code. We just don't have to keep scrolling up and down for us. Okay. So I'm going to set this seed and replace that GDP variable just to make the coefficients a little bit easier for us to look at. I've already created that measurement error. So I'm going to run the original regression. This is where scaling it. Okay, now I have a number that's a little bit easier to look at, right? 60,000 approximately. If I then run this regression of GDP with a variable that has this non-classical measurement error, right? It depended on the value of X. We'll see here, well, it looks like it might be attenuation bias, right? Because my estimate is just going to be a little bit lower. But we'll work through some examples. I'll prove to you that doesn't have to be the case. It all depends on what type of covariance or what type of correlation your measurement error has with your X variable. So this would be the idea. Originally, we had that BMI. People were over-reporting it the higher their BMI was. Well, what if instead we had this measurement error, which was completely random, but then a component was also that it was lower for higher BMIs. So if I create this measurement error, generate my new variable that includes that measurement error, and then run that regression with not the actual BMI values, but the measurement error BMI. Notice now instead of 60,000, I end up with 68,000. So this is where, depending on what that relationship is of X to the reported measurement error, it could increase or decrease my coefficient. I don't know. Okay. Is that clear what I'm doing? Yeah.
What's the plus 0.1 plus 0.2 like times?
Yep. That's my way of artificially baking in that measurement error is going to have to be correlated with the X value of BMI. Yeah, this is like what is the actual function that relates the measurement error to BMI? In practice, we wouldn't know. Here, we can artificially create it so that we can use the data to kind of prove to ourselves if the measurement error was negatively correlated with BMI versus positively, it would actually end up giving me higher versus lower.
Okay, so you would just use that as an example, then sign switch
Just as an example, we have no idea what that actual sign is going to, well, we might have an idea depending what the variables are, how that measurement error is going to look like, but we really don't know truly most times what that measurement error function is going to look like. In fact, I'll show you a couple other ones here in a second. Does that make sense? So I think the other one I have is now a little bit more complicated, right? So actually you could probably kind of piece through the idea. If measurement error in my BMI value was positively correlated with BMI, that meant that when BMI was higher, I was actually getting higher self-reported values. So that was actually going to be making me think BMI was high when it was actually lower. So when I run that regression, high values aren't going to be as correlated with GDP because they're not actually high, right? So they were supposed to be lower. So what happened? When that was the correlation, our estimate was a little bit lower. Now, when that measurement error was negatively correlated, that meant the BMI values we looked at, high BMIs were actually underreporting. So then anytime BMI was low, it looked like they actually weren't, like, look, they were really strongly correlated, but they actually weren't because BMI should have been higher. So what did we end up with there? We ended up with estimates that were too high, right? Now, I wouldn't ask you kind of what that predicted, if it's going to go up or down, but just kind of this easy thought experiment with, I shouldn't say easy, this thought experiment with some easier functions of what this measurement error is with the X values, we can, I think, seems a little intuitive. It gets a lot more difficult when we start to have measurement error that looks like this. Now I've got a random measurement error multiplied by BMI, multiplied by a positive value. So what is this actually going to do? Well, it's going to take the original BMI and it's going to scale it down a little bit, right? However, that's also going to be interacted with this completely random variable. So what is that going to, it's really hard to conceptualize what that measurement error, how it's going to be related to those X values of BMI. So we can see here, if it's 0.1 or 1.5, if it's 0.1, that measurement error would end up with an estimate that's quite a bit lower. Whereas when it's 1.5, not only is it lower, I get really close to a negative value. Not quite negative, right? But really close. Right? If I generated another set of random numbers, I might see a negative value here. Because really, what is this coefficient no different from? If I look over here at my p-value, 0.55, I can't say this is any different than 0, right? So all of this, I'm not going to make you do. You're not going to have to create these variables, but I'm just using some data to prove to you when we have non-classical measurement error, we don't know what the hell is going to happen to the coefficient, right? Depends on what that relationship is between the measurement error and the X variable. So ultimately, for the sake of this class, when this exists, we just don't know what's going to happen to the coefficient. There's no attenuation bias. We can't say it's going to be closer to 0. It could be, could flip signs, could be even higher. Right? Does that make sense what I'm getting at here and kind of how, what I would ask you guys about? It's pretty simplistic. I won't even ask you guys to do this like in your homework, in your problem set, but just to kind of instill this idea of why non-classical measurement error we really don't like, okay? So the next thing that we'll kind of think about is what if we have measurement error in our dependent variable? So once again, we have some good news and some bad news. So let's say that the actual Y value we don't see. All we see is this Y tilde, right? It's going to be the dependent variable that has some measurement error baked into it. So maybe we somehow, can't record GDP. It's not completely accurate. There's going to be some measurement error that in the GDP values we see from our data set, right? This could be as simple as, what do you think is likely true about the GDP values we have? Do you think it's true down to the dollar? They're probably rounded to the trillion or billion, whatever it is. So even if it's just rounding, that does create random measurement error. So when we have data that is rounded, even if it's not, if it's not the true value, we would call that measurement error. So we'll see why that maybe matters or maybe it doesn't, right? So let's say the Y value I observe is not the actual Y value, but it has this measurement error. So here, for the sake of like space on the slide, I don't write measurement error, but anytime I write the word, that is measurement error. and epsilon would still just be the error that exists from like other omitted variables, okay? So we can kind of think about if we rewrite this, here's the y value we observed, right? So our composite error includes error from the omitted variables, but also the measurement error. Right? So why is this going to bias our estimate? So what's one of the key assumptions that we had with simple linear regression? We needed kind of the expected value of our error terms, given different x values, kind of to be equal to 0. Well, now what is our error term here? It's going to be kind of u, right? So we're not going to have, our errors now are going to be including the measurement error, so we kind of don't have this expected value of our error term being equal to 0 anymore. So I think I've got this here, right? The expected value of our error term may not be 0 any longer, right? So, and that's because it's not the measurement error of the omitted variables, right? That error term, it's the composite error, right? That measurement error included, okay? So we don't know that that's going to be equal to 0. Okay? If somehow that measurement error is completely random in our dependent variable, we're still going to end up with an unbiased estimate. So this is the idea. Once again, if it's classical measurement error, we don't really care, right? However, I shouldn't say we don't care because it shouldn't cause a bias in our estimate. But what is it going to create? It's going to create more noise, right? Just more random variation. So if we think about, this is going back a ways, but if we had just a simple linear regression, we said that was the covariance of y with x over the variance of x. This was like without any added controls. This is, like I said, going back a ways we talked about. Well, the covariance between y and x, right? What am I going to possibly be doing with this added kind of composite error that now includes the measurement error? I'm creating more variance, right, in my variables. Right? So I shouldn't say I have more variance in the x variable, but it's going to cause some more variation in what that covariance I'm estimating is. Okay, so I should say here, we end up with an unbiased estimate. However, it isn't unbiased, it's unbiased, but it's not consistent. Our standard errors are still going to be influenced because there's now just more variation in the data. Okay, so I don't know. I try not to kind of focus too much on the math here. I'll kind of more use the data to actually prove this and kind of show this to us. But, you can think of an example. If I had drug use was my dependent variable, and I had some dummy variables, which is whether or not they're a law enforcement officer. Well, if I have some dummy variable or some measurement error in my drug use, as long as that's just completely random, doesn't matter. If it's correlated with any of my x variables, well, now it's an issue. Because now if that measurement error is correlated with my x values, now the expected value of my error term will also be not 0. So once again, we're not going to waste too much time kind of going through that, and we'll ask you like the nitty-gritty details. But what we are going to do is kind of use some data to prove to ourselves whether or not this classical measurement error matters, what it does, and then kind of what if it's non-classical. So here, once again, just to make sure we're all using the same set of random numbers, I'm going to kind of set this seed, and just for the sake of this example, let me see, did I call it something different down here for us? Probably not. No. So I'm just going to copy and paste this again. And I'm going to drop the old measurement error just to make sure we're starting out with the same values. It's not really going to matter. Even if you generated different values, you'll end up seeing the same things going to play out. So we'll kind of scroll down here. So now what I'm going to do is instead think about, what if I were to run this regression of GDP and BMI, but instead of having measurement error in my BMI, I'm only going to have the measurement error in my dependent variable, or GDP. So it's just going to be that the GDP value I see is the actual GDP with this additional measurement error, right? Just completely random. So I'm going to run these lines of code. So the first one, we should hopefully see that same coefficient of 60,000, right? That's the actual data. When I've created some random measurement error in my y, notice what happens to my coefficient. It's exactly the same. Didn't matter that there was random measurement error in my Y value because it wasn't correlated at all with the X values. It wasn't correlated at all with what the actual Y values are. My coefficient is still the covariance of Y with X. That hasn't changed, right? If my measurement error is random, even if I'm using this Y that has the random measurement error, that covariance, X would be completely uncorrelated with that additional random error. So this would be the same. The measurement error is in my dependent variable. So what's going to be true about the variance in X? It remains the same. So I should still see the exact same coefficient. Okay. So now when I'm looking at that coefficient, I see the exact same value. Yeah.
So is our error term on both sides of the equation the same?
The measurement error?
Yeah, the measurement error.
Yeah, so it's just a different way of rewriting this, right? So you're thinking about if Y does include the measurement error, if I was making predictions, I'd make predictions using the same coefficient, same X values. There would be the same error that exists from omitted variables, but now I would have to add in whatever that measurement error is.
So because it's on both sides of the equation, take the what did we just set the bias?
Oh, thinking about what the bias was that exists?
Yeah.
Yeah, because this measurement error, right, is kind of, it's almost like this. We're almost like controlling, this isn't technically quite correct, but it's almost like you're controlling for the measurement error, right? So you're still picking up the relationship between X and the actual Y values because you're accounting for the fact that there is measurement. Now, you're not creating a new variable. It's baked into your dependent variable, but you could go through like a mathematical proof where it shows like, like I said, it's not technically the right way to think about it, but it's an easier way to think about it that it's almost like you're controlling for the measurement error. So you end up seeing the exact same effect that you didn't have it in the variable. Does that make sense? Okay. Now, what it does do is it just creates additional noise. It's a random, right? There's just these random values added into my dependent variable. So notice what happens to my test statistic. Well, it looks like it's pretty similar here, right? If we were to kind of, I think here I've got a pretty large sample size. So I think I've got another example here where we might be able to kind of point this out. So let's say I've got, let's go back up here. And let me just do another example where I create more. So I'm just going to create measurement error again, but just more noise, just more random. So we'll go down here. There we go. Oh, I have to drop this because I'm recreating it. So drop my GDP measurement error variable. And then run this again. So now I've still got measurement error. It's just a lot more random. Notice I end up with the exact same value. So it doesn't matter if I have more random variation, I still end up with that same coefficient estimate. Okay. Any questions on that idea before we keep moving? So ultimately, if it's classical measurement error in the independent variable, we said we care, but not as much because it's attenuation bias. If it's classical measurement error in our dependent variable, we really don't care because it doesn't cause a bias in our estimate at all. Okay. Now, if it's non-classical, so here's where I'm going to take that measurement error, and it's going to be multiplied by the actual Y values. All right, so now it's not random. The measurement error is going to be higher when GDP is higher. So if my measurement error is not classical or it's not random, it depends on the Y values. Now, when I run that regression, where I'm using that new GDP that includes the non-classical measurement error, notice here, my coefficient's not even close to what it should be, right? Here, I've got negative 542,000. It should be 60,000. We know that was the original coefficient from the actual data. So if we have non-classical measurement error in our dependent variable, once again, similar story, all bets are off. We can't say what's going to, or at least for the sake of what we've covered, we can't say what's going to happen to that coefficient. So I guess the end story here with a bunch of math that we don't really need to, I've got stuff in the slides here, but I'm not going to ask you questions on it. Really what this hinges on is that classical measurement error is always preferred to non-classical. non-classical measurement error, we have no idea what's going to happen to our coefficients. If we have classical measurement error, if it's in the independent x right-hand side variable, we know that's just going to make our coefficient smaller. If it's in our dependent variable, we know our coefficient's actually just going to stay the exact same. Okay. All right. So are we at in time? All right, perfect. So I'll go through maybe I think was what more of a fun example, and we'll think through how some of these issues could exist in the data. And I've got some data stuff to go through it. And like I said, hopefully I have a little bit of time. I'll kind of open up that problem set if it's working. So got this old example. I use this in my 370 class as well. But there was this, you know what the Literary Digest is? You guys might be getting too young. So my grandparents had these. They were like these little like magazines that like would come every month or something, and they had like world events and things like that. So they had this back in the day, they're even more important. So they had this idea, they were going to predict the 1936 election, take all these surveys and then send it out to people and be like, hey, look at this. We're telling you what's going to happen in the upcoming election. Right? So 1936, Alf Landon, which great name. I don't know why he doesn't get talked about more. They had 10 million survey cards that they got back. So they have a huge sample size. So what should be true about the predictions they can make? What are they almost definitely going to find if they were trying to make predictions? Sample size goes up. What happens to my test statistic? So sample size is higher. Test statistic is actually going to go, my standard errors will go down. Test statistic goes up. P-value gets smaller. More likely I can reject. I should be able to reject easily here, right? So they were like, oh, we made this prediction. Al's going to win in a landslide. Right? 57% of the popular vote. Well, clearly they got it wrong, right? Alf Landon was not one of our presidents. So what went wrong? Well, there's really two things that were going on here. So we've got both a selection and non-response bias. We want to think about either one of these anytime we're looking at data. Okay. So if I'm looking at a selection bias, this is thinking about who is in my data set, right? So if I go out and ask people, right, I send out these surveys, who am I more likely to over-select in sending out those surveys? So at the time, the only people, in order to have a subscription to the Literary Digest, they had to, the way they got these names to send out to these mailers to people, you had to have a name in a telephone book, and you had to have a car registered to your name. In 1936, who is this? People who are really wealthy. Right? So my sample is going to automatically over-select wealthier individuals. So when I look at the results, whoever wealthier individuals tend to vote more for, that's what my sample is going to predict. That was a selection bias. I was over-selecting based off the way I collected this data. Okay. Now, wealthier people back then tended to vote more Republican, and so that predicted that Alf Landon, the Republican candidate, was going to win. Right? So who owned cars, who owned telephones? There's this paper, and I might have, I think I have a link in the slides. If not, I'll add it in and re-upload them because it is kind of interesting. This was done, I think, in like the 90s. They went back and found like a bunch of people who were these surveys and then like surveyed them again. And what they found was people who owned cars and telephones who actually voted for Landon, about 53%. So even though their prediction was 57%, they weren't that far off. Now, if you only owned a car, you only owned a telephone, not only was this wealthy people, if you, let's say you didn't have a car, but you only had a telephone, where did you likely live? So in 1936, if you lived way out in, I don't know, Spencer or Bedford around here, did you probably have a phone? No, you're out in this rural county. They don't even have phone lines to a lot of those places back then. So if you only have a telephone and no car, where are you likely? A large city, right? So not only do we have a selection issue with selecting wealthy people, the fact that you need to have both a car and a telephone, it's likely we're not going to end up seeing people that are kind of out in these rural areas, right? So people that only had a car or only had a telephone, about 60% of them actually voted for Roosevelt. Now, these people didn't end up in the sample because to be in the sample, you had to have both. They were cross-referencing these names. Okay. And then if you had neither, 73%, so this is like low-income rural people, almost all of them, I mean, actually not all, 73% voted for the Democratic candidate. So nobody here ends up in our sample we're definitely going to have a bias estimate. So the selection bias is something we want to be concerned with anytime we're thinking about, well, where did this data come from, right? You know, anytime I ask for student survey, like I ask you, I've done a couple of this, like where I ask you, like, what's the hardest, or what would you like to see more of? When I look at that data, what do I probably always want to kind of keep in mind? I mean, I probably don't have a huge selection bias in terms of if I teach this class again, I'm going to be teaching a similar makeup. But if I were to teach this class and it was like open to every major, what have I definitely over selected by asking you guys those questions? Econ majors. So if I try to teach this to just a broader group, my sample data, I can make estimates just for econ majors. So this selection bias, what is it going to be connected to that we talked about Tuesday? One of the validity types we talked about, I'm probably not going to have external validity, right? Whatever group I've over selected, I can make accurate predictions for that group. But whatever group wasn't selected in my data set, I'm not going to be able to take my results and really make statements outside of that. Okay? So here, similar idea. I could accurately predict the outcome of the election for people who own cars and telephones. I can't for everybody else. I can only use my predictions for the group that ended up in my data set. So that's why I want to make sure I don't have these selection issues. Okay? And then an easier one I think to think about is anytime we're collecting data, we might have a non-response bias. So in this example, what they ended up saying was when they sent out these 10 million surveys, they only got 2.5 million back. So they went back and asked people, and I forget the reason in the paper. I should have reread it before today's class. But if you own a car and telephone, your likelihood, so they sent them additional surveys and found that if you were going to vote for Landon, you were 35% likely to return this additional survey, but people who voted for Roosevelt, only 7. So for whatever reason, the response rate for people who ended up voting for Landon to any survey was almost twice as large. Now, I guess I think part of this was like, the reasoning they gave this was like stay-at-home moms in 1936 who, right, they don't have a lot of other things going on. If they're wealthy, that all their time, they'll respond to a survey, right? But people who are like more likely to vote for the Democratic candidate, lower income, they're scraping by, they don't have time to return any survey. So that was, I think, part of their explanation. And here you can kind of see, it doesn't matter the non-response bias, how they would have got these names. For whatever reason, the people that ended up voting for Landon in every one of these categories were always more likely to respond to a survey. Maybe it has something to do with people who tend to vote Republican, tend to view surveys as like, their response matters more or something like that, right? But for whatever reason, we're always going to end up with a non-response bias here, which is the people voting for the Republican candidate were more likely to respond to our survey. So our data is always going to have more people who vote for the Republican candidate. Right? So once again, we fall victim to kind of that kind of non-response bias, right? So I don't know, kind of an old fun example of that. We can kind of think about this when we're talking about data. So once again, when I collect data from you guys, who am I getting a non-response bias from if I ask you these in class? Anybody who's not attending, right? So the results I see may look very different than if I really were to like force you to give me an answer or actually collect every single person who's enrolled in the class. I'm getting a non-response bias in that I'm not getting responses from people who aren't here, basically. Okay. Let me see. What else do I want to say here? I don't think I want to go through too much of this just based off of time. No, anything I want to say? I think I've got something in here. Maybe we'll go through this. No. I might save some of this for next class because I do want to help you out with this problem set. So we might extend this data issues to be a little bit more kind of bleed into Tuesday. Anything that left that we haven't talked about won't be anything that's on that quiz, so don't worry about that. But we'll kind of finish up some of these topics on Tuesday's class, where kind of similar to this non-response and selection bias, I'll talk about what if we just have missing values. So what if we just have random missing data? And I'll kind of run some simulations. I think it's the reason why I want to do it is not so much something I'm going to quiz and test you on, but I want to show you kind of the power of Stata. So towards the end of the class, I know that this might not be the last class you take. If you do take any additional kind of, if you go to grad school or if you still are here and you want to take an additional stats class, you might start to do things with programs that are a little more like this. So I'll show you on Tuesday how to run some simulations, right? So this is kind of cool in that like I can generate a ton of different random sets of values and then run simulations based off of those values to kind of prove to ourselves things about the coefficient estimates or the standard errors. You could do a similar thing for running simulations and trying to predict, I don't know, stock price values or whatever it is, okay? So we'll look at some simulation stuff on Tuesday, as long as, hopefully, my files have now updated. And they haven't. So, well, we'll see. Maybe they have. So I know that they'll be here. So let me pull them up here. And I'll kind of hopefully walk us through. I've got to minimize all of this stuff. There we go. This works. Won't do it. I'd like to. Well, maybe we'll have to pivot here. All right. Well, maybe we won't be doing this here. That pisses me off. Let's see. In fact, let me